Hi everyone, welcome to my YouTube channel. Today the topic of discussion is finite square wave potential, and this is the part 1 of the lecture. There will be 2-3 more lectures on this topic. So what is a square wave potential or finite square wave potential? Previously we have discussed about infinite square wave potential where the walls of the potentials extends to infinity, but here we have a finite potential, that is the value of potential is minus v naught for a particular range minus a to a and 0 everywhere. This is the graphical representation of the potential. V naught is a positive constant. Here both bound and scattering states are possible. We have already discussed about bound and scattering states in great details. So we know the bound state means whose energy is less than 0 for most of the cases. Now let's discuss about the bound state. In the region x less than minus a, this region, the region left to the point minus a, where the potential is 0, you can see from the graphical representation. So the Schrodinger equation becomes minus h square square by 2m d2 psi by dx square equals to E psi. Or if we take the constant part to the right hand side of the equation, we get minus 2me by h square psi on the right hand side, and we are writing k square as minus 2me by h square. And note that k is positive here because we know E is negative, so the value k square or k is positive. Solution of equation 2 is psi equals to a e to the power minus kx plus b e to the power kx. We know this is standard form of the solution of these kinds of equations, but it blows up at x equals to or x tends to minus infinity. We are discussing the equation in the negative x region left to the point x equals to minus a, where the wave function extends up to infinity, minus infinity, and we know that the wave function must be 0 at plus minus infinity to represent a physically realizable state. But if we put the limit x tends to minus infinity, the solution blows up. So we have to put a equals to 0 and our solution becomes psi equals to b to the power kx. Now if we put the limit x tends to minus infinity, we get psi equals to 0. So now let's move to the middle region, the region where the potential exists, where Schrodinger equation becomes minus h square square by 2m d2 psi by dx square minus v naught psi equals to ex. d2 psi by dx square equals to minus 2m e plus v naught by h square psi. Just taking the constants and the potential part to the right side of the equation, and we get d2 psi by dx square equals to minus l square psi, where l is root over 2m e plus v naught by h cut, and we know that e has to be greater than v minimum, otherwise the solution will not be normalizable. Though E is negative here, but magnitude of V naught is greater than E. We know that the energy lies somewhere between this region. This is the 0 level and this is the minus V naught level. Energy lies between this region, and we can see here that V naught, the magnitude of V naught is greater than the magnitude of E. So E plus V naught is a positive quantity, and that's why L is also a positive quantity. So solution of equation 3 is C sin Lx plus D cos Lx. Here I am using sin cos functions instead of e to the power ikx, e to the power minus ikx, because we know that if the potential is even function and the solution is either even or odd, that's why we are using sin cos, because determining even and odd functions are very easy with sin cos functions. Similarly, in the region x greater than a, and the potential is 0, and the solution looks exactly like the solution to the left of the point x equals to minus a. But here we have to put the limit of x tends to infinity. So the same argument goes here. If we put the limit, the wave function blows up, but if we put g equals to 0, then we are fine. So the wave function becomes psi equals to f e to the power minus kx for the region x greater than a. As we can see that the potential is an even function, so the solution must be either even or odd. I have told you this already. So we just have to impose boundary condition at x equals to plus a point, and the other side is simply psi minus x equals to plus minus psi x, plus for even and minus for odd wave functions, and that's all. We get the complete solution. Now first let us work out the even solutions. Psi x is f e to the power minus kx, d cos lx and psi x for the three regions. The first one is for x greater than a, and middle one is for the range 0 to a, and we are taking cos because cos is an even function, and we know the wave function in the region x less than 0 is the same as in the region x greater than 0. And to get the wave function in the region x less than 0, we just have to take the wave function in the region x greater than 0 and write minus x instead of x. That's all. We get the wave function in all the regions. The continuity of psi x at x equals to a says f e to the power minus k equals to d cos la, and continuity of d psi by dx says minus k f e to the power minus k equals to minus l d sin la. Here the potential is finite, so psi and its derivative both are continuous across a boundary. Now dividing equation 7 by equation 6, we get k equals to L tan La. As we know that k and L both are function of energy, so equation 8 is the equation to determine the allowed energies. To simplify this equation, let us write Z equals to La. Z is a constant, and Z naught equals to a by h cut root over 2m v naught. This is also a constant. We know the values of k square and L square, so let us calculate k square plus L square. We are putting k square equals to minus 2m by h cut square and L square equals to 2m into e plus v naught by h cut square. So we get 2m v naught by h cut square, and we have already assumed that Z equals to LA. So L equals to Z by A. We are putting that value here, and from here we can see that root over 2m V naught by H cut equals to Z naught by A. So instead of 2m V naught by H cut square, we can write Z naught square by A square. Then we are taking the Z square by A square part to the right side of the equation, and we get K equals to root over Z naught square minus Z square. From equation 8, we know K equals to L tan LA. So multiply both sides by A, we get K equals to LA tan LA. Why we are multiplying this with A? Because we have the value of K in terms of Z and Z naught, and we know LA is Z. So the equation becomes Z naught square minus Z square root over equals to Z tan Z. Now we are taking Z common out of the root over, so we get tan Z equals to root over Z naught by Z square minus 1, equation 11. This is a transcendental equation and must be solved by a computer by numerical methods, or we can plot this graphically and solve it. If we plot tan Z and root over Z naught by Z square minus 1 on the same grid as a function of Z, the intersection will gives us the solutions, and we know that Z depends on energy, so we get the allowed values of energy. Now let us consider two cases. The first case is wide and deep well. We know Z naught equals to A by H cut root over 2m V naught. It is a measure of the size of the well. If Z naught is very large, the intersection of two curves occur just below Zn equals to n pi by 2. Let me show you the graph. We can see that the intersection is occurring just before the n pi by 2, just before it. So we know that Z equals to LA, and we have solved the equation and get Z's value as n pi by 2. We are putting that value here and putting the value of L 2m E plus V naught root over by H cut. Now squaring both sides, we get this equation. So from here we can determine E plus V naught equals to n square pi square H cut square by 2m into 2a whole square. On the RHS of equation 12, on the right hand side of the equation 12, we precisely have energy of infinite square well with length 2a. We know that the energies of a particle in a infinite square well is given by n square pi square H cut square by 2m a square, but if the length of the well is 2a, we get this equation 12, precisely the right hand side of the equation 12. But only one condition is there, that n is odd here. In case of infinite square well, we have n equals to 1, 2, 3 up to infinity, but here we only have the odd values of n, and we will have the even values when we solve the wave function for odd, that is for sine. We will do it in the next lecture. So for v tends to infinity, that is a very large well, or you can say an infinite square well, we have infinite square well energies. This is very interesting. And the second case is shallow and narrow well. If we decrease Z naught, that is if we weaken the potential well, there are fewer and fewer bound state. That is, if we decrease the value of Z naught, this point is the value of Z naught. if we decrease it further, this is the value z0. If we decrease it, it will come closer to the origin, and if we decrease it too much so that its value is less than pi by 2, then at least one intersection will be present, at least one. So for z0 is less than pi by 2, we only have one bound state. No matter how weak or how small the value of z0 is, we will always have at least one bound state. Now let's normalize the wave function given by equation 5. We have the wave function this equation 5 psi x, and here we can see some constant f and d. Let's determine the values of this constant, and we know normalization is very easy. The probability of getting the particle over the whole region is 1. We are just doing the same thing here, and we are taking psi as even function for this case. So instead of integrating it from minus infinity to infinity, we can integrate it from 0 to infinity and multiply it with 2. So put the value of psi in this equation, and we know that the value of psi is different in the two different regions. From 0 to a, its value is d cos lx, and from a to infinity, the right part of the point x equals to a, its value is f e to the power minus kx. Let's put those value in this equation and we get this. So let us take d square out of the integral, because this is a constant, and we know 2 cos square lx is 1 plus cos 2 lx, and the integration of e to the power minus 2kx is e to the power minus 2kx by minus 2k, and the limit is a to infinity, and the integration of 1 is x, and cos 2lx is sin 2lx by 2l, and the limit is 0 to a. And after putting limit, we get 1 equals to d square into a plus sin 2la by 2l plus f square by k e to the power minus 2k, equation 13. Now from boundary condition 6, what is the boundary condition 6? The continuity of psi at x equals to a point. We have the equation f e to the power minus k equals to d cos la, and f equals to d to the power k cos la. Using equation 14 in equation 13, we get 1 equals to d square. The first part is the same, and we are just replacing f square by d square e to the power 2k cos square la, and e to the power 2k will cancel out with e to the power minus 2k, and we are left with this equation. Now we are taking d square as common, and we are writing inside the bracket a plus, instead of sin 2la we are writing 2 sin la cos la, and then cos square la by k. We know that k equals to l tan la from equation 8. We have just written that value instead of k here, and breaking tan la in sin la by cos la, we get the last part of the equation as cos cube la by l sin la. Now if we take cos la by l sin la as common, we get sin square la plus cos square la inside the bracket, and we know this is 1. So the equation becomes 1 equals to d square plus a cos la by L sin LA. Now divide by cos LA in the last part of the equation. So we get A plus 1 by L tan LA, and we have used to replace K by L tan LA with the help of equation 8, and we are replacing it back. So the equation becomes 1 equals to d square bracket A plus 1 by K. So d becomes 1 by root over A plus K. From equation 14 we know that F equals to d to the power K cos LA. So if we put the value of d, we get the value of A as e to the power K cos LA by root over A plus 1 by K. So the complete solution for bound state is e to the power K cos LA by root over A plus 1 by K e to the power minus Kx for the region x greater than A, and cos Lx by root over A plus 1 by K for the region 0 to A, and just put minus x instead of x in this wave functions to get the wave function in the region x less than 0. So that's all for today. Thank you for watching this video. If you like my video, please subscribe and share it. See you in the next lecture.